Hi, my name is Jason Biggs, and I'll be talking about the new molecule functionality in version 12. My name is Jason Biggs. I've been with Wolfram Research for about a little over 2 years now. I came in to join the team at Alpha and develop content related to chemistry step by step. And then I've gone from there to develop the molecule function. Let's look at this. Let's just look at the outline of the talk, a little bit of a motivation, talk about what we've done with chemistry in the Wolfram language so far. Then we introduce the molecule, go over the various input forms, the different ways that you can make a molecule, go over stereochemistry, how you would input this, how you would read it out, something that's been sorely missing in... yes! There we go. What's a good size? 150, 125? Okay. All right. So the Wolfram language will finally handle stereochemistry in a very robust way. The molecule is an object that has a lot of properties. It's got lists and counts that we can go over. Let's see. Then we'll talk about molecule patterns and substructure searching, which I think is one of the most important parts of the molecule package. We'll talk about how you can modify a molecule, how you can change it once you've created it, how you can embed it in 3D, generating new coordinates for a molecule from scratch, which is another one of the really cool things about this package. We'll go over a few really cool, all right, I'll come up with different adjectives, a few interesting examples. We'll look at file imports and then some future topics, the things that you're going to ask, do we do this? And I'm going to say, no, maybe next time. And then some of the experimental functions that we haven't hammered out just yet, but that you might find if you dig deep into a context. We're going to enable dynamics. Why not? Let's live dangerously. Okay, so in the Wolfram language, since version 6, we've been interested in supporting chemists. We have import-export. You can import PDB files that describe a protein. You can import an MOL file, which will otherwise known as a mole file. So you can you can put in the coordinates for a molecule, the number of atoms. Like if we just took that guy and said text, you could see what's living in the file. Yes, why not? There we go. So this is what lives inside of a mole file. And then now, starting in version 12, when you do that, you will get, yes, a molecule. So, but the old behavior was when you would import a mole file, you would get a text, an image, either a graphics or a graphics 3D. And so we're moving beyond that. Let's see, also since version 6, we've had chemical data, which is a part of the Wolfram knowledge base where we collect information on entities. Propane, there's an entry in our database for propane that has lots of experimental properties like combustion heat, the van der Waals constants, all of these things for about between 40 and 50,000 chemicals. And so that's great. Also, more recent is the entity value, where you can access the Wolfram knowledge base directly using these little yellow blobs called entities. And has a very nice interface with entity value, how you can query for multiple properties, multiple entities, get it back in a nice data set. We also recognize the fact that our knowledge base is limited. It's going to have a lot of, it's not going to have everything, in fact. So we create a service connect to PubChem, so you can have access to all, let's say, I think around 100 million records are in PubChem. So you can just query their API using the nice service connect functionality. You ask it, hey, what do you know about INCHI equals 1s over ClO2 C2-1-3? And it says, hey, I know a lot. And there it is. Sorry. Let's see. So very recently, we introduced the Wolfram data repository, where we can take data sets that are out there in the public domain and provide a nice, easy way to access them. So this would be the GDB9 data set with over 133,000 chemicals, featuring up to 9 heavy organic atoms. So carbon, nitrogen, and you can download this as an entity store, and you can access it that way. And I created 3 of these. This guy has 107,000. This one about 20-something thousand. And then finally, we've got Wolfram Alpha, where you can, where I join the picture. You can ask Alpha lots of things using a natural language. How many carbon atoms in 5.46 kilograms of propane? It'll give the answer. If you do that on the website, it should give you a step-by-step and walk you through how to get to that answer. So to a large extent, so here we have a lot of step-by-step solutions for chemistry. But when I was creating these, like this one, so let's see, this step-by-step, can you tell me what atoms inside adenosine are aromatic? So first we look at all the atoms, we grab only the ones that are in a ring, then we decide, no, these guys are going to be sp3, so they can't join it. And then we walk through the rules, counting the electrons, and we decide in the end that these are the aromatic aromatic atoms. And when I was doing this, it made use of a lot of the graph functionality in Mathematica, but also I found that I needed to use external tools. Tools that were special built to work with a chemical graph where annotations are very doing substructure searching, looking for vertices with a particular property, like atomic number 6 or something like that. And so that's when I started to really look toward having a computable object, as they say, a first-class member of the Wolfram language. So that is what the molecule is. So one thing that people are going to wonder is, what's the difference between the molecule and chemical data? And so the main point is that the molecule does not rely on any curated data. You could disconnect yourself from the internet, delete the chemical data packlet, and you could still compute a wide variety of information about any chemical. So here I make a molecule, I give it just the chemical name benzene. It's going to parse that. It doesn't look it up in the knowledge base. It just parses it, and it knows that's benzene. So let's see, I do that. And we look at the input form. It's got a list of atoms, a list of bonds with their bond types. And that's all we need to know. So now at this point, we can go back and say, if we wanted experimental information, look at the molecule. It's got a smiles string here. We could take that, go to PubChem. Let's see. So we've still defined our PubChem, so let's ask for the compound properties. And here, this is M smiles, so it's asking for this molecule M, asking for its smiles. I just evaluated in place, and it becomes that. So now I enter, and look, wonder how good the internet is here. Right, so there we go. So this is what PubChem is able to tell me about this molecule. And if you look here, they compute the Inchy string, the Inchy key. It's the same that we computed because we're using the same Inchy library to do so. Right. So that will give you access to experimental data on any molecule that you might make. But with a molecule, it's very easy to create a molecule that nobody has ever heard of. So starting with so I'm not going to go off script just yet. I will be going off script, but let's make it through a little ways. Right. No, I've got a little timer here. Okay. But I do think it's important that the molecule is robust enough that I don't need to stick with the script. Last year, I presented a lot of the same stuff, but it was not so robust. And I went off script a couple of times, and we saw some streams of error messages, but that's not the case today. Okay, so we could define a list of atoms like this. This is just an oxygen atom, carbon atom. Here we have a nitrogen atom with a positive charge. So in order to add that, to annotate this N, we use the atom head. And we annotate this oxygen with a negative charge. Then we have a list of bonds where the first argument refers to the index, the position in the list. I'm going to move this guy maybe up a little bit closer. Okay, so we evaluate the list of atoms and bonds, and we can create a molecule from that. If we want to, we could visualize it. We could even visualize it in, so when we did that, the 2D coordinates, the structure diagram was generated on the fly using a set of rules, essentially similar to the rules that a graph uses for its graph layouts. Except here we know that when chemists look at a molecule, they like for angles to be 120 degrees. They like for benzene rings to be shaped a particular way. And so using those rules, and similarly, we can generate 3D coordinates on the fly. So there we go. So if you wanted to, you could omit the hydrogen atoms from that list. You could just take the same list, take any hydrogens out, same with the bonds, and recreate the molecule. They have different expressions. They're not going to be same Q. One is going to be much bigger than the other, but they are the same chemical. They're going to have the same properties everywhere. Just because there are no hydrogens in the list of atoms here doesn't mean that the resulting molecule has no hydrogens. They were put in there because carbon likes to have 2 bonds. Oxygen likes to have 2 bonds. And if you create a molecule with only 1 bond to carbon, then we'll fill in the remaining gaps with hydrogens. But that's let's see, that is a configurable behavior. You can create a molecule from an entity. So when we look to that knowledge base, we've got propane here. What we do under the hood is we call entity value, querying for all of these different properties. We get a list, and we create the molecule from that list. And so if you look at it, we actually queried the knowledge, the 2D and the 3D coordinates. So if you look inside the expression, you'll see it's got both the structure diagram coordinates and the atom coordinates already filled in. We'll talk more about whether a molecule is chromatic coordinates later. Let's see. So you can see that if you created the molecule from the entity or from the just from the string, then they're equivalent. Right. Some entities in the database are not going to have all of the information necessary. Like some things can be a chemical entity but not a molecule. So polymers, for instance, polybutyl acrylate describes a class of molecules where there's a repeating unit. And so that's not one molecule. And so it's not going to have any of the molecule data. And so molecule is going to tell you that it can't do it. One thing that I find really exciting is the opsin parser. So what this allows us to do is to parse almost any valid chemical name into a smile string. So there's an internal function here called name to smiles, right? And then we can take that chemical name 2-methylpent 1-ene and convert that into a smile string. And from that smile string, you can create the molecule. And so this, I believe Stephen might have used this for his example in the talk. So long chemical like this that gets parsed right away. So let's see what the smile string. Right. This happened to me a second ago. All I did was hit Apple C. Right. Now let's go back to full screen. Yes, okay. Right. So if you wanted to look at the smile string that underlies this, you could do NTS and so this is what actually is all the information you need to create the chemical graph. Likewise, for this big, long monster, you can create it, plot it, all very quickly. And then finally, there's the smile string, which kind of underlies all of that. We've had smile string in import and export for quite some time now. And what we do there, when you do an import string, you can import it as a list of rules. boom. And then if you feed that to graph and give it a particular kind of graph layout, you can get a decent approximation of the molecule. I believe this is supposed to be caffeine or something closely related there. You could have taken that smile string now and just feed it directly to molecule, and it'll populate all of the vertices of the graph, all the attributes. You can just take that smile string and go crazy with it. You can just put a big long list of C's in here to create a huge ring, put a parentheses here, and do the same thing all over again. And so this is how easy it is to go off book. Like, there's most likely nobody's ever has synthesized this particular molecule, and they want to. But you let's see. But the tools here, we can definitely create lots of molecules that people would like to synthesize and have synthesized, or haven't synthesized but would want to because they'll have a certain set of properties. I'm just showing off the tools here. Let's see. Yeah. So there's some examples here about mixing and matching and jumbling up smile strings to create weird new molecules that you try and create 3D plots from. And it's actually very decent at generating these structures. All right. So, as I mentioned before, one thing that's really been lacking in chemical data, and that once this comes out, we should fill in that gap in chemical data, is stereochemistry. When you do, let's say, chemical data, adenosine triphosphate, right? So this it's going to give us back a 2D structure diagram, and it's not in any way going to tell me about the stereochemistry. So this is a chiral center right here, meaning there are 4 different ligands attached to this carbon, which come off in a tetrahedral arrangement, and the exact nature of those ligands, be they clockwise or counterclockwise, can really have an influence on the chemical activity. So now, if we did the same thing with the molecule, let's see, molecule plot. Yes. So what that tells me is that we have 4 defined stereocenters here, and what it tells me is about the relation 3D. Yep. So what it does is it tells me on which side are these oxygens and these hydrogens on the 5-membered ring. And that can drastically influence the overall shape of the molecule and how it behaves inside a cell. I got one of the first things I did when I came to the company was I got a bug report about this particular molecule. Our 3D structure was completely wrong. And I said, came to me, and the user really questioned my chops, my chemistry chops, and whether I was the man for the job. But I'd like to think we're doing better now. So how do you enter a molecule, right? So here is a simple example. These molecule expressions can get quite large, so I'm just going to look at a simple example here. So one with 4 carbons, 10 hydrogens, and an oxygen. Let's see. Look at this in 3D just for a second. And you see it's this carbon right here that is the chiral center. He's got 4 different ligands, and they could be arranged in different methods, or in 2 different configurations. So the way that we enter that is through an option for the molecule. It takes a list of associations where we tell it what type of stereochemistry we're describing here, what the value is. For chiral centers, what we've chosen to do this is we describe one atom as being the stereocenter. That's the gray one that I'm pointing at. We describe one atom as the fiducial atom, the atom from which you look down, and then the ligands, 3, 5, and 9, let's say that they're bam, bam, and bam, are going to come in either counterclockwise or clockwise. So this is our rather verbose way of writing out stereochemistry. You could also just put two @ if you find this method to be very readable. So that encodes the same amount of information, but just in a less human readable form. So that's encoded in the smile string. So we can take the exact and say clockwise instead of counterclockwise, and it shows up differently in the plot. We can ask them for their chirality, their CIP, con-angled prelog. Where's Bob to correct me? Oh, okay. Let's see. The CIP chirality value here is S or R, and that has to do, well, we could go to general chemistry to learn what that is. Well, no, okay, so what that is, what we're doing is we're describing things in terms of local stereochemistry, the local configuration around this atom. If I wanted to describe the global stereochemistry, the absolute stereochemistry, I would need to step back from the stereocenter and give a rank to every single atom in the list. This would be 1, 2, 3, 7, 9, 2. And then, once you've done at the configuration around the stereocenter and ask, do the atoms appear in order of increasing priority clockwise or counterclockwise? And that's what determines R or S. So R or S is a computed property, whereas the local stereo configuration is an intrinsic property, something you feed when you create the molecule. So we can create those two. Let's see, we'll call them counterclockwise and clockwise. They are not equivalent, but if we change the same test to be enantiomers, then we get a true. And so what that means is that these two molecules are non-superposable mirror images of each other. You can look, when you generate the coordinates, you can look and see that the yellow, purple, and green atoms appear in clockwise versus counterclockwise in the two configurations. So the 3D coordinates that are generated, the stereochemistry that you entered. Likewise for double bonds. So with a double bond, let's see, do I have a plot? Yeah. So here's a double bond. Everything around it is going to be in a plane. And what we're talking about here are these two chlorine atoms that are in the double bond. Are they on the same side or are they opposite side? So that is the stereochemistry support for the molecule. We can also pretend that it's chemical data for a little while, and we can give it properties. Molecule, so we define a molecule, then we can ask for its smile string, the same way as though it were an entity. You can ask for its inchy, and there's a whole host of computed properties which we'll get on the screen. Yeah, so these are just used in machine learning applications. So there's going to be quite a few of that aren't of interest to everybody, but like this guy. Right. So it's a nice big long list of numbers that you can use in some type of machine learning. We'll attach it to some net in the near future. Let's see. So you can use a molecule value if you want to get multiple properties for one molecule. You can use so we can also query for the properties of atoms. So we want to know the atomic number of the fifth atom. This would be the syntax we use. We could also use atomic number 5. Right. We could also query for computed properties. So this is the Gasteigger partial charge. So here I'm asking for the Gasteigger partial charge of 6 and 7. And they're returned actually very quickly. Yeah. Right, so atom list for the molecule. Let's see. So we create a molecule, it's benzene. Another one, sodium benzoate. Wait, why did I create 2 here? Yeah. Okay, so we make a sodium benzoate. It's a nice example here because it's got it's got it's got charges on it. So we ask for the atom count of M. Okay, that's very interesting, right? So there are 15 atoms. Atom list. All right. But you can also give atom list a second argument that's a pattern. I want the atom list of M, but only give me those atoms whose formal charge is not 0. The way that we construct an atom pattern is a rule. So the formal charge is except 0. So that points me to the oxygen and the nitrogen. If I wanted to find out where those occur in the molecule, I say make the second argument a rule. So here we go, atom list, mol, pattern goes to property. So our pattern is this atom object. The property in this case is going to be, and ignore the fact that I didn't learn how syntax information works until too late. That will be fixed. So that tells us that those occur at positions 9 and 10 in the atoms list. Okay. We want the formal charge greater than 0. So it's this sodium, and there's one of them. If we ask for the formal charge greater or equal than 0, it's all except for one atom. Likewise here for, you can search for the atomic number. You want atoms with the atomic number greater than, atoms with an atomic number greater or equal than 6. Bond list and bond count work the same way. So you create a molecule here. You can ask for its bond list, and it's essentially going to give you the second argument. But then you can ask for only the double bonds. So there's just this one double bond here between atoms 7 and 8. I never know quite when to mention this, but I've made it so that the molecule plot by default uses tooltips to tell you where the atoms are. So I know that this is atom 7 and 8. I found it to be really useful. So you could ask for the bond list and give the second argument just as double. You could likewise use a pattern bond with an underscore double. And those are equivalent. Turn the same result. But then what gets really fun here is the different kinds of pattern here. So here I'm going to use a pattern to represent a single bond, a bond between one atom that is a member of a ring and an atom that is not. And I don't want to get any results that have a hydrogen attached. So I run this and I get 3 bonds, and I can highlight those, and it shows me that indeed those are atoms between those are bonds between heavy atoms where one is in a ring and one is not. You can get a list of all the bonds where both atoms are in a ring and highlight it like this. Right. And so here I'm just showing that you can apply a style if you like, or use the automatic styling. No, so this one is kind of neat too, right? So you want to find a bond between an atom that has a positive formal charge and a negative. And so that's going to, let's see, didn't define that molecule. And so it's going to point out this bond where we have a positive and a negative atom bonded to each other. All right, and so bond queue. Why did you give a whole slide to bond queue? It's a small little function, but the point being it didn't fit in the other slides. Very often when you're doing working on these things programmatically, you need to know if something is a bond or not. So you write a pattern, question mark bond q, or underscore question mark bond q, something like that. And so it's useful. M is this. Are atoms 1 and 2 bonded? Yes, they are. What about atoms 1 and 3? They are not. And if you give it a bond order, then it better be correct, or else we will say no. Okay. So that brings us to molecule pattern, which may change. Molecule pattern and fine molecule substructure. So, right. So a molecule pattern has basically the same structure as a molecule. It's a list of atoms and a list of bonds. But the main point here is that it doesn't need to be a full molecule. You can have a molecule pattern can consist of just two atoms that have an aromatic bond between them. A molecule, because aromatic bonds need to be in a ring, but it can be a molecule pattern. So if I wanted to find a pattern to match a single sulfur-oxygen bond, I could write that in two different ways. I could write it as a molecule pattern with a list of atoms and a single bond, or I could just write it like we were doing on bond list as bond SO. And I can use find molecule substructure to find all occurrences of this pattern inside a particular molecule. And in this case, we see that those are indeed true, equal. If we use the SMARTS pattern language, then we can find a third way of writing the same molecule pattern, which is this S tilde O, where the tilde represents any kind of bond. But the reason we need a molecule pattern head is because then sometime you might want to find a substructure containing more than two atoms. So here is a pattern for sulfur with bonded to two carbon atoms. And we look inside of M for that pattern, it's there, and we can plot it. And so these are the matches, where you have a sulfur bonded to two different carbon atoms. You could define a pattern to match any n-membered ring. So this would be a ring pattern for, let's see, so ring pattern 6, this is the way I've defined this here, ring pattern 6 evaluates to have 6 blanks and then bonds in between. And if you search for that inside of this molecule, that's what you find. You could define a ring pattern where for 6 atoms, where one of them has to be a nitrogen. And again, it comes back relatively quickly. You could take a more complicated and look for rings with 4 atoms or rings with 8 atoms. And yeah, so this is what we get. And then you could also highlight this in 3D. All right. So I'll fly through this example, but I think it's really neat. You could define a pattern for a bond between an atom with a negative gas dihedral partial charge and an atom with a positive partial charge. So then you search inside this molecule and you find that the sulfur here has a pretty big positive charge, and it's drawing electrons away from the neighboring oxygen and nitrogen atoms. And so this is the structure that matched that pattern. Right. And then you might want to modify your molecule. For the longest time, I was calling it modify molecule, and so it's taken me a while to get Molecule is not, and I know the name is confusing, the molecule is not atom Q, so you can modify it in place. You could take a molecule and then just do a replace all and replace the word aromatic with single, and you get a completely different molecule. So what's happening here is replacing this phenyl group with just a cyclohexyl group. You could say, I want the 15th atom in that molecule to be phosphorus instead of nitrogen. And that evaluates to be atom of P, and it shows up in the molecule. Right. So there are various different ways that you might want to modify your molecule. You can add it's not the most interesting of modifications because it just adds an atom, it doesn't add a bond. If you want to add an atom and have it bonded to something, you add bond, oddly enough. So we take a molecule, we add a bond between atom 6 and an oxygen, which is new. And so that's how you can add in a new atom that is bonded to. I skipped ahead there. I don't think going over delete atom, delete bond, probably not that important. This is interesting though. So modify a molecule, transform the atom coordinates. right? So where did I define M? We'll just leave it like that. So M is this. So we make a copy of M, and we transform its atom coordinates using a translation transform. And then we can plot the two of them together, and we see that indeed has happened. So the transformation function here can be anything. It can be a scaling transform, and you can end up looking molecule. Let's see, I want to get to here to replace substructure, because I think this one's really neat. So let's say you've got this molecule, right? Let's bump up the, right. But you want to look inside that molecule and find a carbonyl, or not just a carbonyl, but an ester, right? And you want to replace this C double bond O with CFC. So it's molecule modify, M, replace substructure, old goes to new. And so as you see, the oxygen was replaced by a fluorine, and the neighboring oxygen also is now a carbon. You could take a molecule and replace a benzene group with a cyclohexane. Right. Yeah, that's good. We've got to replace list also. There's plenty of nice examples in there. But I think that in the interest of time, we should just move on to the fun stuff. So you could take a molecule modified, start with norbornane, and end up with camphor. So we define the two molecules here. Now, we can go from one to the other just by adding 4 bonds. In reality, we're adding 4 bonds plus atoms, but the add bond is the easiest way to do that. We add a methyl group here, methyl here, and a double bonded oxygen there. So we start with norbornane, we add the bonds, and is this equivalent to camphor? Yes, it is. So it's not quite a reaction. I think the chemical reactions are going to be really interesting, but they're going to have to wait for next. So this is more of a manual modification. So this one I thought was fun. Again, we're going to be making some molecules here that probably nobody would ever want to, but just for the fun of it, because we are, it's a Gedenken experiments, right? Start with cyclopentane. We take that and we replace every occurrence of hydrogen on the molecule with benzene. And you ask yourself, surely you won't be able to embed that. You won't be able to come up with coordinates for that. Well, this is what we got. And you might say, man, those guys are a little crowded. Every one of those carbon has 2 benzene rings attached to it. Okay, well, let's replace the interior cyclopentane structure with a cyclodecane. That is, replacing the inner 5-membered ring with a 10-membered ring. And this one's tricky because let's see. In our previous use of replace substructure, we were replacing the substructure and the replacement had the same number of atoms. Here we're replacing a 5-membered ring with a 10-membered ring. And in order for it to do this intelligently, we have to tell it the attachment points, the correspondence between atoms in the pattern and atoms in the replacement. So we want 1 goes to 1. We start at the beginning, and then for every index of the pattern, we increment the replacement index by 2. So 2 goes to 3, 3 to 5, like this. Wait. Right. Oh. All right. Okay, well, I'm gonna have to fix that example. But so it was working just a little bit ago. So what we have here, so we took this interior 5-membered ring and we replaced it with a 10-membered ring. Right. So embedding molecules in 3D, this is a big deal. Generating coordinates on the fly for molecules is not an easy thing to do. So So a molecule, when you're creating one, you can add the coordinates directly to the expression, or you can use the coordinates that are generated automatically. If you provide them, they're going to be different than what you would get than the automatic coordinates. And so if you provide the coordinates with the expression, we will use those. If you want to not make those coordinates automatic, if you want to generate coordinates for them and place them in the expression, you can use molecule modify with the compute atom coordinates. And so what this does is it uses the method described in this paper to embed the molecule. It compute a distance bound matrix based on the chemical graph. So what this does, so you want a matrix, this n atoms by n atoms, and the element, so between, let's say there are two carbons that are 4 bonds away from each other. Well, we know that the bounds for carbons that are 4 bonds away from each other, they're going to be between 3 angstroms and 7 angstroms, depending on how floppy those 4 bonds are. So that's going to have a loose bounds, whereas carbons that have just 1 bond between each other, they're going to want to be between 1.3 and 1.6 angstroms. And so you create the distance bound matrix, then you find a random distance matrix that satisfies those bounds. And then from that distance matrix, you generate 3D coordinates to match the distance matrix. Check that it's not insane, that it has reasonable energy. And if it does, then you correct the structure using torsion angles that were trained on actual experimental data from the Cambridge Structural Database. So all that is happening when I say M is this, and molecule modify and compute the atom coordinates. And so now we have them stored as a quantity array with a unit of angstroms. And you could convince yourselves that they're identical to what you would get if you use the automatic coordinates. So you can also use compute atom coordinates to generate random conformers. So we can do molecule modify, compute atom coordinates. Random seeding goes to automatic, and so therefore it'll be truly a random seed. Do that 100 times in about 1.5 seconds, and you can look at the distribution of energies for the conformers. And so these are the MMFF energies. But if you wanted to, then you could use that force field to minimize the structures, and you get a much tighter spread. You could even use select to pick only those molecules that have energy below a certain threshold. You could also say you had a molecule that had no stereochemistry in it, elements, but it had a structure, 3D coordinates. You could use those 3D coordinates to generate the stereochemistry. And here in this example, I start with a molecule that has stereochemistry, compute its coordinates, then I remove the stereochemistry, which all that is doing is taking away that option. Stereochemistry elements goes to blank. So therefore, now in the diagram, we don't see any stereochemistry, no wedges or dashes. But it does have coordinates, right? So this guy has coordinates, but no stereochemistry. So now we look at those coordinates and we regenerate the stereochemistry just from the coordinates. And we see that the end, what you get is equivalent. Right. Energy minimize atom coordinates. This uses the Merck molecular force field to find a local minimum geometry. So say you take a mol equals molecule of water and look at its bond angle. This uses the automatically generated coordinates. These are fast coordinates. We get them really quickly. Comes back with a bond angle of 106 degrees. But if we take that same structure and we minimize the energy according to this force field, we get back something that has 103.9 degree bond angle. So the experimental gas phase bond angle, I think, is 104.5. But basically, you get the bond angle that is corresponding to your force field. So this force field, the MMFF, is going to minimizes to about 104. What I think is interesting is if you take those waters that from which we did not, generate 1,000 water molecules with using an automatic random seed and look at the histogram of the bond angles. They're kind of all over the place. But if you want then, you take those same structures and do an energy minimization, and we see the histogram, the values are a lot tighter. Right. Yeah, those are very, very tight, I would say. So you can also, let's see, it's almost time to go. So you can set the bond length, set a bond angle, right? Even to ridiculous extremes should you so choose. Right, now we move on. This is a pretty neat example. This is in basically every general chemistry textbook. They tell you ethane has this particular torsional potential. And what this is, let's see, right. So here, let's say M equals molecule at ethane. And we can, so this is the potential, oh, right. Right, so you can take that molecule and you can spin this torsional angle, basically. And what it says is when these two carbons are overlapping with each other, then the energy is highest. When they're staggered, the energy is lowest. And that's where you get this kind of potential. And so you can, as you see with these plots, you can get the same type of potential using the molecule functionality. Either by just using set torsion angle directly, you're not modifying any other bond angles, bond lengths, or by using the energy minimize atom coordinates and setting a set of constraints on your the minimization, forcing the torsion angle in question to have a particular value, but then letting everything else relax to its, and you get the yellow curve versus the blue curve. So that's a neat example, I think. Right, we definitely have time for this. Okay, so chemical data sets are oftentimes released D files. This particular one is 3.5 gigabytes. Sean was just talking about how files can just eat up insane amounts of memory by reading them into Mathematica before parsing. And so SDF parsing has gotten a lot better with this. So I'm not going to do it right now, but if I wanted to, in just under a minute, I can take this file and grab let's see, between molecules 10 and 1 million in steps of 100. So that brings in about 10,000 molecules out of that 3.5 gigabyte file. You can look at random molecules from there. You can then, with that list of molecules defined, that list of 10,000 molecules defined, define yourself a pattern for a carboxylic acid. You can then take and search for that pattern using molecule contains Q, select only the molecules in the list that contain the carboxylic acid pattern, and you'll find a little over 1,100 molecules have that pattern. You can then highlight those patterns. Yeah. Right, so what do we not cover? We don't cover chemical reactions. That's something I think is going to be really interesting. So we need a symbolic representation for them. Part of the whole point of this was the molecule is not just an entity or a smile string. We need a Wolfram language symbolic representation for it. And the next step, we need a symbolic representation for a chemical reaction. They could be pattern-based, and then they would apply to a broad range of molecules, or they could be specific, with specific instantiations of the pattern. They could store meta information, the kinetics, spectator compounds. My own background is in quantum chemistry, electronic orbitals, like this. So that's a direction I'm very interested in moving next. So a few other things that I think would be really interesting, stereoisomer enumeration, tautomer standardization, tautomer enumeration. These are coming very, those are hopefully coming in the next release. So, right, and then I'd like to acknowledge the fact that these open source toolkits are underlying a lot of the functionality here. The Opsin parser is really amazing. We started using it in alpha a long time ago, and it can just blazingly fast some really interesting chemical names. And so I don't have enough. Well, yeah, time is kind of stretched for me. I've been focused on this for a long time. Like, I just want to point out these slides that you can explore yourselves, because everybody has a copy of the beta. These experimental functions for generating resonance structures, looking at symmetry information. You can grab the point group and plot. Well, I can do that one real quick. Does anybody have any questions? So there we go. We just created that. Then we can find all of its planes of symmetry. All right. Does anybody have any questions? Okay, we'll talk more about the symmetry information. Fingerprint similarity is also something that's really cool. You can create a molecule here, another molecule here, and you can get their fingerprints. The fingerprints of different varieties, atom pairs, topological torsions. They come back as bit vectors, right? Just a bunch of ones and zeros. And then you can find their similarities. You could search for, use that as a distance function in a nearest application, finding all the searching within a data set for the nearest matched chemicals and whatnot. All right. So, but really though, any questions? No. Okay. Let's see, I mean, by job security, right, it should never be done, right? There should always be more, there's always more to do. What's that? Yeah, no, so we should be able to wrap this up within a version or two, I think.